So we are very happy to have Dr. Ekta Chaubey from University of Turin. Ekta did her PhD from University of Mainz, right, Ekta, in Germany. And this is her first postdoc. And today she is going to actually talk about master integrals, which appear in the calculation of TT bar glue amplitudes. So Ekta, please go ahead.
Hi, thanks, Ambrish, for first of all inviting me for this talk and also for this very nice introduction. It's a pleasure talking about my work in front of you all.
Okay,
So,
one more thing. Actually, we will be recording your talk. Is it fine? Actually, I
yes,
had mentioned.
yes,
I think.
yes, yes.
Okay. Thanks. Go ahead.
Okay, thanks. So the topic of my talk today will be about, as Ambrish already said, will be about master integrals, which contribute to the amplitudes for two-loop planar TT glue process, but also including master fermion loops. You will be shown why it's a complicated process, but this talk will be roughly based on this paper which we published just recently with my collaborators Simon Badger, Bayu, and Robin. Actually, yeah. Before we actually start this talk, I want to give a preview of what's coming in front of you all. So I will be talking about higher order loop calculations, which are crucial to make precise theoretical predictions. I will try to show how complicated it is to obtain these ingredients to make this predictions even more precise. And I will try to ask this question, do we know the properties of these ingredients? For example, is there a class of functions which we know about? And last but not the least, how easy it is to numerically evaluate these ingredients? Because after all, that's very important to actually do all the checks, because yeah, it's like a black box. Unless you can check it, it's not verified. So with this pre-introduction, the outline for my talk today will be first, I will try to give a bit more motivation and introduce my setup. I will talk about the tools and techniques we use in such computations. Then I will go on and talk about what are these two-loop integrals I'm actually evaluating. And I will also talk about some integrals we actually evaluated in this paper, which were not available before. Before summarizing, I will also explain the numerical evaluation of all these integrals, and in particular the functions which these integrals are written in terms of. So with this, let's start. So we all know actually that the precise understanding of top quark is a very important ingredient in understanding the fundamental forces. Now, the complete two-loop amplitudes for top quark production has only been computed numerically so far by this group of people. And one of the major reasons why that is so, why that is actually only computed numerically, is because once you start including these fermion loops, which basically once you start including the internal masses, a more complicated class of functions start to appear in the evaluations. And sometimes these functions are not even understood well. Today, we are going to look at the important ingredients, as I already said, for computing these analytic forms of top quark pair production. In particular, I will analyze the function basis of the master integral. So if you do not know what are master integrals, you do not have to leave already. I will try to explain what are these master integrals. And I will also explain the presence of these complicated functions I said. So what are these special functions? Namely, these are called elliptic, and they appear due to the fact that I'm trying to include fermion loops. Basically, I'm trying to have massive internal masses, basically. I will discuss the new master integrals and also the functions they evaluate too. I will also explain that actually these new master integrals are also fortunately or unfortunately belonging to these special functions, which are elliptic. And at last, I will try, as I said already, I will also explain the numerical evaluation of these master integrals and the complications therein. So to set up my process, I'm going to talk about a general scattering tt-glue process, and I have two management variables there. All the external legs are mass are on shell, and so there are two invariants S and T for this process, which are shown here. I may also change variables, and I can actually deal with X and Y in place of S and T. But basically, there are two invariants. You can call them S and T, or you can also call them X and Y, whichever you prefer. So the color decomposition of a leading color tt-glue amplitude looks something like this. So at general L loop, the amplitude is given by this formula, where I think you might be aware of all of this, but basically T is the fundamental generator of SU-NC, where NC is free for QCD. So the partial amplitude here is further decomposed in terms of at each order like this. And all the ingredients I'm going to talk today are actually going to come from this. So in this formula, NC, NL, and NH are the number of color, the number of light quarks, and the number of heavy quarks. The number of heavy quarks I have is just top quark, so it's 1. And the only complicated or the only non-trivial stuff which there was in this paper was actually coming from this. And this is also the culprit of these of the presence of these internal these functions which come because of the internal masses, because of the fact that you included the internal masses. So I will be talking about these A to NH basically. Now, roughly, this is just a rough sketch of how I come from amplitudes to master integrals. So a general strategy for a two-loop calculation looks like this. So you have a bunch of, so you write an amplitude at a particular order as a sum of different diagrams which contribute to that process. Now you want to arrange them in a nicer form so that you can write them in terms of something which we call ISPs, which are independent scalar product. And in the space of ISPs and loop momentum, and which looks like this, Ci, Gi basically. So these are the sum of diagrams which have the same propagator structure. Now, this is just to say that the amplitude is written in terms of a sum of diagrams which have the same propagator structure, but it can happen that these all diagrams are not independent. There exist relations between them. How we actually identify, how we make use of these relations is with the help of something which we call IDP identities, which is nothing but integration by part identities. So this is the identity which we can actually apply on this, and this tells us that all these G's are not actually independent. There are relations between them. Using these identities, you can actually find the minimal number of independent integrals you want to evaluate. You say that once you evaluate these minimal number of independent integrals, you can say that you evaluated the amplitude at this A2 basically. So these independent integrals is what we call the master integrals, which is denoted by Mi here. So once you have the master integrals, you can actually see how the pole structure looks like. And yeah, you can arrange like this, and you get something which we call finite remainder. And the A0 and A1 are just like, so this is just the divergent structure, so universal pole structure basically. So you might ask actually, like, yeah.
Ekta, so in this last line, so earlier you have this pole structure which is 1 over epsilon 4 to 1 over epsilon E0, but then after that you have this I2, I1 and F2.
Yeah, these are the matrices actually. So this is not, you can arrange it. So these are matrices actually.
Okay, so what does it mean that I2 would have basically more than one pole structure?
Yeah, I mean the ones which come from A0, which will be coefficient of I, will be in I2, and the one which come from A1 will be in I1. Yes. You can, yeah, you have to rearrange it basically to get this pole structure prominent.
Okay, and you are saying basically this can always be done at 2-loop level.
Yeah, I think so.
Okay. Okay.
And this A0, A1 are the tree level and one loop contribution?
Yes.
Okay.
Yeah, so you can actually ask, so these are actually sometimes these IBPs identities. So just getting these IBP identities is a non-trivial task by itself. And the proof of that is that there are various implementations available in the market, which go by these names: fire, Kira, light red, air, reduce. And actually it's still going on. So sometimes it can be really complicated to find to IVP reduce basically an amplitude in terms of master integrals and getting these structures DI basically. Like this is also a non-trivial task by itself. So we use something which is called finite flow for our IBP reductions, and we get the master integrals for our amplitude. These master integrals are the ones which I'm going to focus for the rest of my talk today. So I am interested in solving the master integrals. Now, you may ask, what do you mean by solving the master integrals? What I mean is that I am interested in the Laurent expansion of these integrals in epsilon, where epsilon is the dimensional regularization parameter. So once I have these MIs, I want to write them down like this, basically. And you can actually, there is a proof that it's very easy to tackle these problems, the problem of solving the master integral with the help of differential equations. So the idea is you differentiate the master integrals with respect to the invariants you have. For example, in my case, I have S and T. I can derivate the master. I can derivate them with respect to S and T, and then solve this differential equation for each of this master integral by providing the boundary constant. And it's as simple as that, basically. So you get the differential equation, you solve it by providing a boundary constant. It looks very simple, basically. And yeah, in the field of solving master integrals with the help of differential equation, there also has been a lot of progress already. So to explain it further, let's suppose, as I already said, if I have a master integral, a set of master integral I can derive them, get the matrix, which looks like this, and you have to use basically all the invariants. So this A will be given in term like this. Basically, you have to know AS, AT, and if there are more, you have to get. Basically, it's just the total derivative of I. And the condition that these differential equation, these one forms A have, so these basically are called one forms, and they have to satisfy the integrability condition, which is given by this. And here, this is just a normal wedge product. Now, the idea is that often it happens that when you actually derivate the...
Sorry, can I ask a question here?
Yeah.
So this integrability condition is not automatic?
Actually, it's not automatic because, for example, if you do not have, suppose if there is a bug in the IBP program you're using, it may actually happen, and it has happened many, many times, that it doesn't give you the minimal set, but there are, it gives you one or two more master integrals. And then there are actually relations which you have to identify from somewhere else, which actually reduces this number further. So if there are relations between the bases which you are using, then this condition will not be satisfied. This is a check actually to to make sure at least that it's the correct system you are dealing with. But actually, this also doesn't guarantee that the number will be minimum, but at least this is something you should really start with before even beginning to solve this system of differential equations for these master integrals. So yeah, this is actually important. That's why I mentioned it here, because sometimes actually this doesn't happen.
No, so sorry, KP. I'm just basically asking the same question bit, and then you can continue. See, you are saying basically that you want minimum master integrals, but
Yeah.
independent of like whether it's minimum or maximum, the question that whether this integrability condition is always satisfied, like what is the problem with that? I mean, you will end up with basically a set which is larger. What is the problem with that?
So if you try to if you have a basis and they're actually not independent, you will see that actually this is not satisfied. That's what I'm trying to say.
So no, that's the point basically. This integrability condition, if the basis set is independent, then this is always satisfied.
Yes, that's what I'm saying.
Okay. KP, please go ahead.
No, but if there are more than the required number, then they can't be linearly independent.
Yes. Yes,
Yeah,
the
that
INFN program does give it. Actually, so for example, I can even tell you that if you use fires here, it can happen that it gives you one or two more number of integrals actually than Kira. For example, which one of them is actually the correct one? You will obviously assume that Kira is the correct one, but you actually have to check. So unless you can actually reduce the extra number of master integrals in Kira from fire, then only then you can check it, right? But basically, I'm saying that these IBP programs are often buggy, and you have to make sure this is just a check which you actually have to do before you start actually. And if there exist relations between these integrals which you claim to be independent but they are not, then it will not be satisfied. For example, for this Topbox, if you see one of my papers actually where I computed Topbox, actually this was actually one of the problems we had, that we started with the minimal basis, but when we finished everything, at the end we actually, just before publishing, we checked the integrability condition and it was not satisfied. And the reason for that was that in one of the sectors, by sector I mean a set of diagrams which have the same propagator structure, in that the number of master integrals was not minimum, so it was giving 5, but actually there were only 4 independent integrals. So so once we actually found the relations and substituted it, actually the integrability condition was satisfied. So there have been actually cases like this.
Okay, thank you.
If they are not independent. Okay, thanks for asking. Okay, so
Ekta, I have just one more question. So in this expression for A, why you have only differentiation with respect to S and T and not with respect to M, the masses?
Yes, so that's a very good question. So you can actually take you can set mass to 1 and you can actually restore it later on. So if you have ST and M squared, you can actually divide everything by M squared and just deal with basically 2 independent independent invariants, basically independent variables you want to deal with, basically. And you can restore this M squared later on.
Yeah, so this is if all the masses are the same, right? You're projectivizing the equations.
Yes, here there's only one mass.
Okay, go ahead.
So once you have the basis, suppose we have this basis which the IBP systems give, you want to solve this differential equation, but you might actually see that it's not the most optimal basis you want to work with. For example, you can have square roots in the differential system, and having square roots is actually not nice, basically. Like, it's not very convenient. You want to change the variables such that the square root goes away, like it becomes it's not there anymore. And for example, this initially I showed you this from s to x. That's one of the examples which people often do to remove the square root. And that's one way where you want to change. You can either change the variables which you want to work with, or you can also change the basis. So you can do a transformation. You can go from this set of vectors I to a set of vectors j, and you can do a transformation such that you get a new differential equation. So this is basically, in some sense, your desirable differential equation you want to work with. And of course, a dash is related to a by just this equation. You can also look at like gauge transformation, basically. So I mean, this is all looking very familiar, right? Like change of basis, having a transformation, and yeah, solving the differential equation, finding the boundary constants, and so on. So
I wanted to clarify this one more sentence about this integrability condition. The integrability condition is a necessary condition for solving di equal to ai, right?
Yes.
It is necessary. It is not like it's if it was not satisfied, you cannot find I. You cannot. I mean, it's not like there is any choice or anything like that. And so the integrability condition is simply obtained from di equal to ai by one exterior derivative.
Okay.
Right. Is that right, or you are just agreeing with me?
No, I mean, it is right. I am saying that so this I for me is the master integral. So master integrals by definition are independent. So if you want to solve master integrals, you have to have the independent basis, basically. So you are saying that, yeah, once you have this, it will satisfy. These are the same things.
Okay.
Okay. So we discussed that we have a differential equation. You want to integrate them, and you want to write them in terms of long expansion as a parameter, epsilon, basically. Now you might ask, what are these objects which appear? So how do you write these ij's at each order of epsilon j? So in order to discuss that, I want to, for just one slide, I want to mention a very formal definition of what we call as iterated integrals. So for any lambda belonging from 0 to 1, the k-fold iterated integral of, so for example, let's say I have omegas, k omega, so k1 forms, which are given by omegas. Now the k-fold iterated integral along some path gamma is defined very formally like this. And this object I gamma, which I call the iterated integral, is what I will be writing down my master integrals at each order in epsilon, basically in terms of. Now here, these f are basically this pullbacks to this the integral I started with, basically from 0 to 1. Now this is a very formal thing, but the reason I mention it here, it will be clear very soon. So iterated integrals are actually something which come very naturally when you solve a system of differential equations where you arrange them as sectors. So for example, so when you have a diagram, you will have so for example, let me just define a sector. As I already said, sector is something which you have, where you have the same set of propagators. Now, the same set of propagators might also have second power of propagator and so on. So all of these integrals which have the same propagator structure, they might differ by the propagator power, but they all belong to the same sector. Now, the thing which comes naturally from IDP and this thing, they will also have a subsector of that. By subsector, I mean you actually pinch the propagator, so the diagram becomes smaller. It has less number of propagators. So when you solve them, when you solve this set of integrals arranged like this, the iterated integrals are things which come naturally from this. It might not be very clear, but actually it will be clear soon, later in the talk. So basically, this is the object which I need to write down the differential equation in terms of, unless I know something very, very simpler, basically. So what are the things which we might know from kindergarten, basically? the objects, the functions which we know are, for example, logarithm.
Could I ask a naive question on the previous page, please?
Yeah.
No, previous to that. Yeah, previous. So when you differentiate with respect to one of these Mandelstam variables, you would expect, does that change the number of the power of the propagator?
Yes, yes, it does. It's a sum of.
So in other words, the master integrals are a basis for all integrals of the class that contribute to di vector.
Exactly, yes.
And those are not dependent upon the powers of the propagators. Somehow, when you differentiate, it's still some kind of linear basis.
So actually, this is so, I said it just like this, that di equals to ai, but it is actually also not very simple to get this. So basically, why di can be written as ai is, I think, what you are asking. So for example, if you have a propagator, you differentiate it, it is obvious that you will have actually increased number of propagators. But the fact that they are actually independent with respect to IDPs, that is actually, you can do the IDPs on this right hand side again, and then you will get this matrix A. Actually, like you can still, whatever you get, even in terms of increased propagator.
Even after you increase the power of the propagator, you can reduce it back to the same set of basis.
Exactly.
Okay. Thank you.
That's how you actually get this matrix.
With some mixture, mixing matrix A.
Yes, it's it will mix actually all the higher higher sectors with lower sectors, like all the diagrams which have all the propagators there, they are mixed with also the diagrams which, for example, just a tadpole or a bubble. These are all, first of all, they are all scalar diagrams.
The only thing that was puzzling me is that if you increase the power of the propagator, that doesn't actually change you to a different sort of class of integral altogether.
No, the fact that they are actually the master integrals, that itself is a statement that whatever you derivate them with respect to from the same, for example, it doesn't matter, you can even derive.
So they are defined modulo integration by parts, so you can therefore maybe go back to different power. Is that okay? Yes. Sorry, thank you, yeah.
No, just you can ask as many questions as you like, basically. So I am now interested in asking what kind of functions I can use to write these master integrals in terms of at each order of epsilon. So the very simple object which we all know is a logarithm, which is given like this. Now you can generalize this logarithm to a classical polylogarithm by going from 1 to any n, and it looks like this. Further, you can generalize this because, and that brings us to something which we call multiple polylogarithms, basically MPLs, and they look like this. Here I generalize not only n but also the x's. Because I have multivariate cases, therefore I need to generalize it to any x, basically. Now, because I'm integrating this sum structure, some series is not the optimal thing I would want. So this is something which we might be familiar with because we know what is a logarithm. Okay, you generalize it to something which is called MPS, but it's still a sum representation. You do not want a sum representation because you are integrating the differential equation. So you want to have an integral representation of the same object, MPLs. And that looks like this. So these G's are something which is the integral representation for the same MPLs. Now these G's and these LIs are actually related. You can also say the same thing, but actually that's not strictly true, but basically they are the same thing. But one is in the sum representation and the other one is in the integral representation. Now, this formula here is defined just for zk not equal to 0, but of course it's also you can also define what is the case when it is actually 0. And these class of functions, these MPLs or G's, are actually well understood, and they are endowed with an extremely rich algebraic structure, and they are very well studied now. And not only they are very well studied, but that is at such a level that even the tools for fast numerical evaluation for this is available. And it's just a matter of fraction of seconds, basically, to have to evaluate anything which actually evaluates in terms of these genes. So these are in some sense simpler objects for me. Now, if this is simpler, what other things can appear there? Now, actually, it's not only that there are actually more complicated stuff, but there can be even more complicated than these objects which I'm going to talk about now. So when we talk about studying the class of functions which are there in our system, we try to identify, we try to see some algebraic structure therein, basically. So we often find that in the system of master integrals, in this differential system, actually you see an elliptic curve actually sometimes. And these elliptic curves are in some sense more complicated than these amperes. Mathematically speaking, these amperes are objects on genus 0, but elliptic curves are on genus 1. So it's more complicated. But let's not go into mathematics today, but I just want to mention that there are some things which are more complicated. They satisfy an equation. So here, omega equals to a square root of a quartic polynomial is the equation for an elliptic curve. So once you see that there is an object in your differential equation which satisfies this differential system, you say that there is an elliptic curve. Now there are various ways to check actually if this is actually an elliptic curve or this is just some bad choice of variables you are dealing with. For example, it can happen that you see a square root of a quartic polynomial, but if you change the variable, the square root goes away, or the quartic polynomial becomes quadratic, basically. And but once you actually verify that this is actually an elliptic curve, you cannot make any change such that it goes away. We say that it is an elliptic curve, and these curves are associated with two periods by definition. So these are also rich objects. They were actually being studied very long back in mathematics, but only recently, as we actually started including masses in our evaluations, we saw that these mathematical objects, which were separately studied, are actually even appearing in physics, basically. And since then, there has been a lot of progress in understanding and even making this at the level of GPLs, at the level of G, basically. But it's actually not at that stage yet. So once you have this elliptic curve, you say that these elliptic curves are associated with two periods, by which I mean they repeat themselves after these intervals, which are psi, which I denote by psi1 and psi2. And yeah, they actually appear in so the dependence of iterated integral, which I said before, on these elliptic curves enter through this appearance of these periods. So once you have the elliptic curve, you want to find what are the periods. There is formula for that. Then you actually, these periods will be the ones which will go in the differential forms for these iterated integrals I mentioned, these i's. So you might also ask that, okay, you have an elliptic curve. Is there an integral representation in terms of which you can solve the differential equation for them? And there is actually by these two group of people, and these integral representation is called elliptic polylogarithm. It is just a generalization from multiple polylogarithms, which are simpler to a bit more complicated objects, which are also polylogarithms, but they're elliptic in nature. By elliptic, I mean there is an elliptic curve and there are two periods, and you have to know what are these two periods to actually get this integral representation for them. Now, these are also now, last year they were also implemented, the numerical routines for them were also implemented at the stage that now they can be evaluated very, very fast. So in some sense, you can say that even they are now within reach of complications. So you can actually solve them easily. Now the obvious question is to ask is actually, is there anything more complicated? And unfortunately there is, and this is actually the thing which I will be talking about now in the rest of the talk. So basically these elliptic polylogarithms, which you also know the properties of, which you also can numerically evaluate, they actually depend, by definition, they are tied to just one elliptic curve. Now, so far in mathematics, there is no object which you can actually write down in terms of when you have more than two elliptic curves in the same system. So in the rest of the talks, I will be talking about a system which is actually which shows that there are not one elliptic curve, but there are three different elliptic curves, and you cannot make them one, you cannot remove them basically, and it's more complicated. And therefore, I will have to resort to just the formal definition of iterated integral to write down these differential equations basically. So I was mentioning before that you can change the basis of differential equation to bring them to a more canonical form. So for the cases of multiple polylogarithm, it is a conjecture, it has been so far always right, that there exists a rational transformation. By rational, I mean the transformation will only contain objects which are rational in the kinematic variables and epsilon basically. So in the case of MPLs, you can always make a rational transformation from your I basis, from your initial IVP basis to any basis you desire, so that they actually come in this canonical form, where basically the epsilon, this dimensional regulator, factorizes completely from the differential equation, this A, basically. Once this happens, you know that these A's are just D-logs, basically. So you can just write them down in terms of polylogarithms once you have this structure. And there are also many packages now which even evaluates for you the transformation which you need to go from the I basis to a canonical form, and even write them down in terms of GPLs. For algebraic cases which involve roots and often which are evaluated to elliptic curves, this canonical form is not it's not there, but it has a different form in this paper by Stefan and Luisa, where they say that actually, if you relax the condition that the transformation from your IDP basis to your desired basis J has to only be rational in the kinematic invariance, but allow them to have also the periods which are transcendental in nature, and also the derivative of the periods to appear in this transformation, then you can have a canonical form for also these complicated cases, basically. With this, all this tools and technology.
Sorry. Can I ask a question?
Yes.
By canonical form, you mean the form for the A's such that the epsilon dependence has been pulled out, right?
Yes.
Okay. And A's only depend on the kinematic variables now.
Yes. So after this completely factorizes from the differential equation, dA will only have x and y or s and t, whichever variables you're working with, only that. As you see here, this is just x log alpha k of x, some factor k basically, but this will not have any epsilon. When this happens, you can actually just write them down in terms of these MPLs of x's basically, and that's why this x was generalized to have any number of x's. So 2, for example, here for x and y basically. So this was all the tools and techniques which people often use to solve.
Sorry, can I have one more question?
Yes.
So this A tilde, now it looks like it will have various singularities in the xk spaces, right? Meaning as a functions of the kinematic variables. So for example, you had this, we still have the integrability condition on A tilde, right?
So this will have poles.
Yeah, it will have.
This will be only, so basically here you will have just one pole basically, and that's why you could write them down like this, the logs basically. I mean, when you derivate it, you will have 1 upon 1 minus alpha k, for example.
So the A tilde has only simple poles.
Yes.
Okay.
Just.
I see. Okay, thank you. Yeah.
So let's apply all of these techniques on actually evaluating something. So now I will be talking about the so-called Topbox, which was for these amplitudes. This Topbox was the source of all the elliptic curves. So this object that you see on your screen is what I call the Topbox. Here, the black solid lines are the massive propagators. So for me, because of the top loop, I'm including ongoing, as I already mentioned, all the external momentum are outgoing and on shell. And I have two invariants, two Mendelssohn variables, S and T. I can use X and Y, for example. And this was actually shown by me and my collaborator in this paper, that this was actually evaluating to 3 different elliptic curves. And therefore, as I already motivated, that there doesn't exist a very nice objects like Gonzalez-Paul logarithm, multiple pole logarithm or elliptic pole logarithm, which you can write them in terms of and also evaluate very numerically very fast. It doesn't exist because these are 3 different elliptic curves. Therefore, we solved all the differential equations for the Martian integrals and expressed them in terms of just iterated integral, these formal objects I which I introduced in the beginning. Now, actually, you might say, why do you say there are 3 elliptic curves? How can that happen? So this is one diagram. How can that happen? So for example, if you pinch a diagram, by that I mean, if you, for example, just remove this 2, and you will see that these basically shrink. And if you keep doing that, these are the all subtopologies which actually contribute to this system, which you need to solve this top box. So you will see that something which is called a sunrise so these sunrises is something which had been studied like in the last century a lot by mathematicians. And you will see that if you, for example, pinch the propagators 2, 3, 5, and 6, you will see the sunrise. Now the sunrise looks like this thing here. And this was known that this evaluates to an elliptic curve. And this then when we started studying it in physics, we actually showed that we can write them down in terms of elliptic logarithms and so on. So one of the topologies, the subtopologies of this top box was containing sunrise already. Now, when you keep pinching it in different ways, you see that actually there are different topologies, and they were actually also having an elliptic curve in them, but it was not the same elliptic curve. So for example, there were these topologies, which actually all 3 of them contained one particular elliptic curve, by which I mean that we could identify a curve in these topologies. In the differential system, we could see that there was a curve, but this curve was different from the curve of a sunrise. And similarly, there was yet another topology, a subtopology of this top box.
So different means not birational.
Yes, as you can see here, this is the curve, for example. You see all these factors here are the first 2 factors are the same. However, the last 2 factors looks a bit similar, but actually only in one of the limits, they actually are the same elliptic curve. If you put S to infinity, all these curves become the same curve. That is the curve of a sunrise. But just like this, not in the limit, there were actually 3 different elliptic curves, and therefore it was more complicated than we could handle, basically, like at that stage.
So sorry. Okay, sorry. I want a clarification about that. You mean that there is no algebraic change of z's?
Yes.
That will take you from one to the other, right?
Yes. Yeah. If you think about something even more concrete, mathematically speaking, there is an object called J invariant for an elliptic curve, which you can actually evaluate, and you'll see that they are actually different. Basically, this evaluates different things, and it just shows that they are not just different forms of the same thing, but they are actually different objects. There was no transformation which you could perform to make this to transform these curves to this curve, basically. I have to say that because it was so complicated and because this was the first time it was observed, the study for making it to understand why this was the case and so on, it's still going on till now, actually.
So I think if you want to translate this statement into the physics, what I think you're trying to say is that different kinematics regions actually evaluated completely different numbers or functions.
Kinematic regions, by which you mean different values of these kinematic variables. Is that
That's
what you
right,
mean?
S, T, and U. So what is the
Yes.
statement that, yeah, how does one
So,
say this in terms of the actual kinematic variables?
So in one of the limits, as I said, in one of the limits, these three curves were evaluating to the same elliptic curve, which was s equals to infinity. There was yet another limit, which was t equals to 0, t equals to m square limit, which was where we saw that all these elliptic curves even went away, and it was just multiple logarithms, which we had to deal with. So these different kinematic values did actually say that the system simplifies. But for all the phase space, for all the values, you do not have this nice simplification, basically.
Okay. Thank you. Yeah.
So now you may say, you might ask actually, so there are these complicated objects, and you do not know what functions, what nice functions you want to write them in terms of, which are even very fast to evaluate numerically. Then how do you actually represent them? Now, just for a comparison, let me show you
one more question. Can I?
Yeah.
In the previous thing, these while these three elliptic curves are not, of course, algebraically related, they now is there some way of relation when if you relax algebraicity, meaning as you were saying earlier, if you allow for dependencies on the periods and derivatives of the periods and so on.
Okay. That was actually a bit different statement. So this was not the same thing. So for example, this was actually to transform the basis in a nicer form where you want to start writing them down in terms of some objects. For elliptic functions, for the integrals which have this complicated objects, you still want to have a nicer basis. Like you have all those curves, but it will be nicer actually if you could factorize this epsilon completely. To do this, we actually there was a conjecture in this paper that actually if you relax this condition that the transformation is only rational, then you can have this nice form of the differential equation for the mass integral. But this is once you have this, you want to see still what the objects actually are.
Okay, I see.
So these are two different things. So this is where you start with actually, like it is very complicated if you don't even do this in some sense, like naively speaking. So you want to factor out this epsilon so you can actually integrate them iteratively from the highest sector to the lowest sector, basically. And to do that, you want to still have this canonical form, so to say, for these algebraic cases. Yeah, but it was just an observation that for these curves, for this topology, in two limits, this simplified to something which we know, the functions which we know very well, actually, which we are very familiar with. But it was not in all of the values of S and T that was happening. So just as a comparison, if I take this, I am actually already not even half. So if I take a comparison of both of these topologies, one without including the internal masses and one with including the internal masses, this was actually computed by this group of people. And they actually showed that this computed just in terms of Gonzalez logarithm, which is actually, for example, G1x is just logarithm of 1 minus x. As I said, these are just very related to the logarithms. But if I do include the masses, I get these objects, these iterated integrals I, and then the kernels, instead of 0x, 0, 1 like this, they actually look like this actually. And here you see that in one of the kernels, there is even a period of an elliptic curve sitting downstairs. Now, so this is for instance, the elliptic curve associated, the period associated to the elliptic curve B. Because there are 3 elliptic curves, I denote them by ABC. So this is just one of the one forms which appear in this iterated integral. And just to give a rough estimate, this is one of the simpler ones which we have in our system. So if you have this, it might also happen that instead of these omegas are the one forms which are actually polylogarithmic one forms. But it can happen that all of them are like this. So what you do not know what you can do if you, for example, have another eta 11a or another eta 11c, where instead of period of b, you have period of a and c respectively. Like if you have all three curves in the same iterated integral, you do not know what functions you want to write them in terms of. So okay, it's not moving. Okay, so the main features of Topbox was that there were three distinct elliptic curves. The system of the differential equation simplified for two points. One was t equals to m squared, and second was for s equals to infinity. For t equals to m squared, they were expressible in terms of multiple polylogarithm, and for s equals to infinity, they were actually expressible in terms of iterated integrals of kernels of sunrise, because all the curves actually became one curve. So,
so can I ask one last question about the previous one?
Yeah.
So isn't it possible that these three elliptic curves actually arises degeneration limits of a genus 2 problem, really?
Might be, actually, might be, yes.
Yeah, okay.
But yeah, I mean, at the moment, there are also, as I said, more complicated objects appearing. This is just one, at genus 1, this is one of the complications which we have, but there are much more, there are even something which is called K3 surfaces or something. I mean, I don't even know how to, what exactly how to explain that, but basically they are even more complicated. So yeah, it can happen that this is happening because of that, but I cannot comment. So I actually do not know how long I can go on. Maybe I skip this. Okay, let me just try to cover as much. So as I already said, I tried to we tried in this paper to evaluate previously missing integrals, and these are the new. So this is the family. This is a Feynman diagram which contributes to for this amplitude, and it leads to new master integrals. And if I just talk about the scalar diagrams, actually this looks like this. And I also as I already said that you want to have all the master integrals, so you will also have the master integrals and the subsectors which you want to evaluate for this system. And we actually observed that most of the master integrals. So first of all, there were 22 master integrals in this family which we had to solve the amplitude, to get the amplitude. Out of these 22, 20 were actually already computed in the literature, and 15 of those 20 were actually even from the same integrals from Topbox. So we could just use the results from there. But these two were really new, and this is how the transformation there looked like. Fortunately, it's not very ugly, but nevertheless, this was still elliptic, because in the subsector of this M22 and this M21, these two master integrals, there were sunrise sitting and another sector sitting, which was actually evaluating to the elliptic curve B. So the upshot is that this M21 was actually having elliptic curve A in it, and M22 was actually having elliptic curve B in it. And the results actually for these integrals to all orders look like this. So just 4 orders, for example, the first 4 orders were 0, starting from the 0th order in epsilon. At the 4th order, a bunch of them were just G's, the simpler ones, but the rest of them were actually these iterated integrals I, having kernels of kernels having periods in them. The one forms have had these periods of A. And similarly for the J22, so J21 is the transformation from M21, which I work with, as I already mentioned here. And for J22, all the ellipticity comes at the 4th order of epsilon of J22. So for example, all of the first 4 orders starting from 0 actually just evaluated to either 0 or g's. But at the fourth order, they were actually kernels having elliptic curves, having periods from elliptic curves B. And they were, most of them were actually from the same topology, which was actually in the top box, but there were 28 additional kernels apart from the kernels of this top box. So last but not the least, I want to spend some time on the numerical evaluation. So as I said, if I were able to write these down in terms of G's or even elliptic for logarithms, the numerical evaluation was easy. But now that is not the case. So we want to actually evaluate numerically these objects I. Now to do that, we can actually use the path decomposition formula to evaluate these iterated integrals. So what is the formula? The formula is, if I have two paths A and B, and such that the ending point of A is the starting point of B, then AB denotes the composed path obtained by first going along A and then B, and then you can actually write the final result like this. Basically, in simpler words, what you can do is, if you want to evaluate these iterated integrals from the space point x0 to y0, x0 y0 to x, any x and y, instead of going just like just from using a straight path, you can actually use two paths, and you know how to. So you can evaluate the contribution of these iterated integrals on these individual paths, and then you have to just patch them together using this formula. This is the path decomposition formula. Now, often it's actually very, very helpful. For example, as I already mentioned, for Topbox, there were 2 points where they were simplifying. So in particular, if I put y equals to 1, which is c equals to m squared, it was actually all the curves were going away, and the result was just in terms of Gonchar-Foy logarithm. So on one of the paths, I could choose the path such that y equals to 1, for example. And then all I have to take care of is just the second path, the contribution from the second path, which I also can simplify, because now it can be, for example, only depending on one variable. You do not have to parameterize basically both of the variables. You can keep one of them constant, for example. And then you can use this formula and evaluate the final contribution. This is the technique which we use to actually evaluate them in different physical phase space, different phase space points. So for Euclidean region, as I already mentioned, these two paths, one where dy was 0 and y was 1, and second path was dx was 0 and x was actually 0. We chose these two paths because on one of the paths, it was just multiple Fourier logarithm, and we could give it to one of the programs which evaluates numerically these functions in a matter of seconds, basically. The properties of the top box made evident which path we should choose to use this path decomposition formula. And for the second path, where, so for example, this path along y, we could, for example, use a series expansion in y. And if the point is very close to y0, you can just use one path. But actually, if the point is farther, you can use either higher series expansion, or you can just use even more paths, and then you can use the path decomposition formula recursively and and get the final result. So this is for evaluating in the Euclidean region, it was actually observed that it was really very simple. This was all the master integrals were checked numerically at this point, and they were verified using sector decomposition in Fiesta. For checking these master integrals at physical point, however, it's not very simple, because you have to cross a branch point, a physical branch point, and then you have to know how to analytically continue these functions. And that's actually not very, very simple, actually. So we use, for that also, we use just the same technique, path decomposition formula. You have to know what paths you have to choose. You want to know where, around which point, if you actually use a series expansion around some point, you want to know where to expand around, so which point to expand it around. while doing that, you have to know all the singularities of the kernel. So once you know singularities, there might be also spurious singularities. So the singularities which are actually not there, but they come just because of your choice of the basis or the differential equation, basically. So these spurious singularities do not affect the results, but actually if you do not take them into account, it can really be, the numerical evaluation can be divergent. So a technique which we often use while making this series expansion is we actually center our expansion point on the singularities of these kernels in our system. So for physical points, for example, this is in this graph, this region here where the point P is where my physical point is. So I want to start from, I am starting from x0, y1, and I want to go to any physical point here. While doing that, I can choose, for example, this path. And because it's a bit too far, and the series expansion around any point will not be, you have to really include, you cannot just use one expansion, you have to choose multiple path segments here. So you can choose, for example, I had to choose just 5 segments and use the path decomposition formula recursively and get the contribution. So one important thing is when you cross this physical threshold. So when you cross from, this is the physical line which brings you to the physical region, you will have to analytically continue all the periods. And that's actually a very non-trivial task. So for this, for the purpose of this paper, actually, because the periods were actually involving two variables, because I had both x and y, we were able to, in a timely manner, we were able to analytically continue both curves A and curve B, but actually we just evaluated the curve C for, we just evaluated using SecDec for this numerical evaluation. This shows how complicated actually the analytic continuation and the whole process is, and also that it is not so just we just studied actually the continuation in the numerical evaluation in Euclidean region and the physical region, but the generalization to all of the phase space points is still not there. It's still not done, basically. So in other words, a stable and efficient evaluation over the whole physical scattering region is still far away. Nevertheless, this was still the first time actually this evaluations were done, and just studying these elliptic curves, the continuation of these elliptic curves is a highly non-trivial task, and we actually, this is something which we still have to work on. So to summarize the results, we were able to continue, analytically continue all the results which involved the elliptic curves A and B to the physical region. For the master integrals containing elliptic curve C, we used Fiesta inside PySecDec, and we compared the finite remainder of the square matrix element at the physical point, which was this. This is the physical point, and we compared it against another group which did an independent calculation, and we found quite good agreement. So just to summarize my talk and to give some outlook, I hope I'm able to convince that this two-loop amplitude for tt-gg with massive fermion loops were actually very non-trivial, and this was the first step in including masses also in evaluation. And while doing so, we had to evaluate also some previously unknown integrals, and I showed that these also contain these non-complicated objects, namely the elliptic curves. For doing the numerical evaluation and the verification that the results were correct, we explored a new approach for a direct numerical evaluation of the iterated integral with more complicated kernels. We also looked at the complications involved in the analytic continuation of iterated integrals, which involves multiple elliptic curves. And there is, because it was so complicated and because we have 3 elliptic curves, there are still actually some redundancies in the correct iterated integral implementation. And to construct a nicer basis of transcendental function is still not there actually, and it's being worked on. Thanks for your attention.
Okay, thanks, Ekta. Thanks a lot for a very nice talk. So maybe we had a lot of questions during the talk. So if there are actually some more questions, we can take this opportunity and ask questions to Ekta. Are there questions? Okay, I don't see any question. So I just basically just had one. Yeah. Yes. Go ahead.
Hello, Ekta. I have a very naive question actually. You said, because of the involvement of that masses in the loops, uh, we have to deal with that elliptic curves, right?
Yeah.
So if we change the basis, can we? But if we change the basis of master integrals, is there any way that we not come across those elliptic curves or?
Actually, I think I also mentioned it during the talk that often it can happen that because of a wrong choice of variables you work with, you might see that the differential equation contains an elliptic curve. But when you actually change the variables, when you try to rationalize these square roots, you see that actually this elliptic curves go away. That does happen, but actually for this sunrise. So first of all, when somebody says that there is an elliptic curve, they have to check this thing first. They have to check that there exists no rational change of variables, which actually removes the square root, which is actually in some sense the generator of this whole elliptic business. You have to verify that this doesn't go away. So if you change the basis and if it goes away, it's actually not an elliptic curve. Saying that, for sunrise, for example, this is actually for sunrise. There is no doubt that this is just not possible because of this because of the presence of three master propagators. They do evaluate to elliptic curves, and there is even proof that you cannot change basis such that it goes away. For other cases, actually, for massless cases, it happens that it might look like if there is an elliptic curve, but it's not there, and you have to then check. I mean, there are various tools also to check that. So, for example, if I talk about more mathematics, there is something called Pika-Fuchs operator, which you can calculate and check what is this operator, and using this. So it's also in some of my papers how I show how to check actually this elliptic curve, that this is really an elliptic curve, and you have to calculate this operator, and that actually shows you that once you try to factorize this operator, you see that it doesn't factorize, and that's a proof that there is an elliptic curve for sure.
Okay, and is there any formula or something like that by looking at the diagrams we can directly know that how many elliptic curves will be there?
Yeah. So it's actually there is so it's actually a very it's a non-trivial question. So it's a very good question. First of all, it's really on the conjecture level that, for example, if you see a diagram, for example, here I see a top box, and I know by looking at it, I know that when I pinch some propagators, for example, here if I pinch 2, 3, 5, 6, I see that there is a sunrise in the subtopology. Now that sunrise will always be there. You can, if you want to solve the top box, you have to also solve the subsectors, and therefore you know that there is at least one elliptic curve. How many elliptic curves are there? There is actually no study so far, because this was really the first time 3 elliptic curves appeared even. And even now they are actually trying to study why this happens and if we can actually write them down in terms of some basis. Having said that when you have actually a subsector where there is a sunrise, that's for sure, it's almost, yeah, it's very sure that you have an elliptic curve. It can happen that no subsector actually evaluates to any of the diagrams which you know that they are elliptic, but it can still have an elliptic curve in them. That you have to check actually. But just by looking at a diagram, it's really sometimes a luck that you can know that this is a complicated diagram or not. But there's no for sure way to knowing that actually.
Okay, thank you.
I have a rather naive question. So this was for 2 to 2 scattering. you have observed some things in the master integral that give you sort of these elliptic curve like structures. So I was curious whether this applies in general to any sort of scattering, say 3 to 3, or is it something that is only constrained to, say, diagrammatic, or is it when we evaluate these integral expressions, I'm seeing these quantities. So
yeah, I mean, I just talked about 2 to 2 scattering processes, but yeah, it is not true that this is really just 2 to 2. Presence of elliptic curves is not even related to physics, actually. Like the curve is actually by itself given just by this formula here. It is just the observation that these appear in physics, and we can use this appearance by knowing what we know from mathematics and write the function, like manufacture the function basis such that we can actually use what is already worked on by mathematicians. So this is just like, you can just ignore all the elliptic curves and so on. But if you are really interested in studying the function basis, which is what we are doing right now, then you observe these elliptic curves, and it's not only for 2 to 2 processes, but for example, now I'm working on 2 to 3 process, and there also, if you have, the presence of massive internal propagators is often what gives rise to these structures. So that's what is more important rather than the number of legs or the process you are having, basically.
Yeah, thank you.
Does that answer? Okay.
Yes, yeah, thanks.
So we have one question in the chat box. The question is, do the same set of elliptic curve appear in case of non-planar case or different set?
So for this Topbox, I didn't evaluate the non-planar non-planar case. It might happen that actually there is no elliptic curves even because it's non-planar, but we haven't actually, nobody has calculated that for this. But if you're asking if in general non-planar cases, if that can happen, that actually can happen, yes.
Okay. Any further question? Okay. So if not, let's thank Ekta once again. Thanks, Ekta. Thank you very much for giving this talk.
Thank you for your time.
Yeah. So hope to basically talk to you at some other time. Okay. Okay. So let's close the meeting.
Okay. Bye-bye.
Bye, everyone. Bye.